Okay, so in this video and the next video, we finally talk about quantum teleportation. I'm sure you've heard about quantum teleportation. You've seen it in Star Trek, how to teleport an object from one place to another. This is in quantum teleportation is in rough analogy with that. So you'll see that there are similarities. There are very big differences. But what is the basic idea in quantum teleportation? So you know that it's impossible to clone a qubit. But in quantum teleportation, you want to transport a qubit from one location to another. And well, one way to transport it is if you have a quantum channel, if you could carry the quantum bit from one place to the other. But it turns out that there's this other way of transporting it from one place to another, which is called teleportation. So let's see what that means. Well, first, here's the setup. Okay, so you have let's say there are two physicists, Alice and Bob, experimentalists. And Alice has created a state which it took her a long time to create it. It's a very interesting state. It's some superposition, alpha 0 plus beta 1. She doesn't quite know what alpha and beta are, but it's just the output of some process that she designed. And now she wants to run this quantum state through some other apparatus, which she doesn't have, but Bob has in his lab. But Bob's lab is across campus, at the other end of campus. How should she get her qubit from her lab to his lab? Or maybe it's all the way across the city. How should she transport this qubit from one location to another? Okay, so one thing she could do is she could try to send it from her lab to his lab. But let's say that these two labs are very distant and it's very hard to transport it from one place to the other. So what else could she do? Well, of course, she cannot really make a copy of her qubit. But what she might try to do is try to figure out alpha and beta and then give that information to Bob. But of course, alpha and beta are complex numbers. Not only do they require, what Alice has to do is figure out to sufficient precision what alpha and beta are. But all she can do is measure the state. And she doesn't, if she measures the state, she does not really get alpha and beta. What she sees is 0 with probability alpha squared and 1 with probability beta squared. Moreover, as soon as she does the measurement, the new state is whatever she saw. And so she can't repeat the experiment. So if she has only this one copy of the state, she really cannot figure out what alpha and beta are. So what is she to do? Okay, so this is where quantum teleportation comes in. So let's say that Alice and Bob were ready for this eventuality. So once upon a time, they set up, they shared a bell pair with each other. So meaning that they have these two qubits. Alice has a qubit and Bob has a qubit. And they happen to be in the state 0, 0 plus 1, 1, in the bell state. Of course, this bell state has nothing to do with the qubit that Alice wants to transport to Bob. So quantum teleportation is this remarkable protocol by which Alice can do something with her two qubits, the one that she wants to transport and the qubit out of the bell pair. She does something to these two. She measures these two. So what Alice does is she takes these two qubits and she performs a measurement. Okay, what's the result of this measurement? Well, she's measuring 2 qubits. The result is she gets 2 bits of information. She gets 2 bits. Let's call them B1 and B2. These are classical bits, right? It's 0, 0, 0, 1, 1, 0, 1, 1. So now she picks up the phone and calls up Bob, and she transmits these 2 bits across to Bob by phone. At this point, you might think, Alice, what did you do? You've destroyed your qubit. Well, now what Bob does is based on what Alice told him about B1 and B2. He performs some single qubit gate, or he actually performs 2 gates on his qubit. Which gate? Well, it depends upon what B1 and B2 are. And lo and behold, what happens is, after performing, so he performs some unitary rotation. It's going to be a simple unitary rotation depending upon B1 and B2. And what happens? Well, what happens is magically this qubit gets transformed to being in the state alpha 0 plus beta 1. So this quantum state, which got destroyed at Alice's end, suddenly reappears on Bob's end. Okay? So in what sense is it like teleportation? Well, it's like teleportation in the sense, on Star Trek, in the sense that, well, you had this entity here on Alice's end, and you perform a certain protocol. This entity disappears, and then you do something on Bob's end, and it reappears at that end. So it's like teleportation. In what sense is it not like teleportation on Star Trek? Well, it's not like that teleportation because it's not instantaneous. Alice does her measurement at her end, she destroys her qubit, and she is left with just this classical information. And now she has to pick up the phone, she has to send this information across to Bob, and it's only after he gets this classical information that he can reconstruct the quantum information that Alice started with. Okay, so in this and the next video, we are going to understand how this protocol works. Okay, and to make this easy, I'm going to break this protocol down into 2 parts. First, we are going to start by making an unrealistic assumption. I'm going to assume, okay, so on top here is Alice's lab. So she has a qubit in the state alpha 0 plus beta 1. On the bottom here is Bob's initial qubit, which is initially in the state 0. I'm going to assume that Alice was able to perform a gate between her qubit and Bob's qubit. This is completely unrealistic, but it will help us understand how to proceed with teleportation. Okay, so she performs a C0. What happens? Well, obviously the state of the 2 qubits after the C0 becomes alpha 0, 0 plus beta 1, 1. Now, what we'd like is, we'd like somehow to do something on Alice's end so that Bob gets left with alpha 0 plus beta 1. And Alice gets left with just a measured qubit. Okay, so what should Alice do? Well, she could try measuring her qubit. Okay, so if she measures in the standard basis, what happens? Well, if she measures and the outcome is 0, then the new state of the qubits is just 0, 0. And what's the state of Bob's qubit? Well, it's just that, it's 0. On the other hand, if she sees a 1, the state of his qubit is just that, it's 1. So alpha and beta just disappear if you do a measurement in the standard basis. So measuring the first qubit in the standard basis was a terrible idea. Okay, so here's an idea. Why not use a different basis? So what basis should we use? Well, let's try the plus minus basis. So now what we're doing is, what Alice does is she measures the first qubit in the plus minus basis. We want to know what's the result of this measurement. So let's write out her state. Let's write out the state alpha 0, 0 plus beta 1, 1. And let's rewrite her part of the state in the plus minus basis. So it's alpha 0 is 1 over square root 2 plus 1 over square root 2 minus. And then of course you have his qubit, which is in the state 0, plus beta 1. 1 is 1 over square root 2, 0 minus 1 over square root 2 plus minus 1 over square root 2 minus, and then his qubit is in the state 1. And so now what we want to do is we want to collect terms. So this is 1 over square root 2 plus times. So plus comes from here, and then you have alpha 0 for his qubit, and then you have plus, and you have plus beta 1. I'm just factoring things out. And then you have minus here, 1 over square root 2 minus times alpha 0. And for with minus here, you have minus beta 1. Okay, so that's the state of the two qubits. If you write the first qubit in the plus minus basis, and the second qubit you leave alone as 0, 1. So now what happens if you do a measurement? So if Alice does a measurement, well, her outcome is either plus or minus. If her outcome is plus, then the new state, well, her qubit is going to be in the state plus, but also his qubit will be in the state alpha 0 plus beta 1. That's great, because that's exactly the qubit that Alice was trying to send to Bob. And now he's got it, so that's great. But on the other hand, if the outcome is minus, then the state of his qubit is alpha 0 minus beta 1. So now what should he do? Well, Alice can pick up the phone and she can call him and say, in this first case she says, the outcome was plus, you've got the qubit. In the second case, she calls him up and says, sorry, the outcome was minus. But then Bob says, you know, that's not a problem, because I have a phase flip gate sitting around. The phase flip gate is the Z gate, and what it does is it changes the phase in front of 1 to minus. And so that's going to take this qubit and restore it to look exactly like Alice's qubit. Okay, so what did we discover? We discovered that if Alice was able to perform a C0 from her qubit to Bob's qubit, then she can create this special state alpha 0, 0 plus beta 1, 1. And then if Alice does a measurement in the Hadamard basis, in the plus minus basis, in the sign basis, then, and she communicates that to Bob, he can apply a correction or not depending upon what the outcome was, and he can recover Alice's qubit. So the challenge is how to create the state without the C0, and that's what we'll see in the next video.